in order to avoid some misunderstanding, then I probably just keep using English if you don't mind. Right? Okay. All right. So the title of my presentation today is when is the best time surfing in California? Yes, the one question is why in California. Last year I was funded by Fulbright, and then I went to the University of Miami in Florida, and I was working together with Professor Brian House at the University of Miami. And then when Professor Samsudin Toha asked me the topic, what I'm going to present, and then I said, well, let me show my recent work on ocean waves. So to make it a little bit interesting, and then I say, let's talk about surfing, even though I'm not a surfer. And well, in Indonesia, we also have some places to serve, but last 4 years we published a paper in the renewable energy is talking about a wave energy assessment around Indonesia, and the resolution we claim to be the high resolutions because that's the highest resolution ever had in Indonesia until now. Okay, let me introduce so this I'm saying that last year I was funded by Fulbright in Indonesia. We had we call it AMINEF. AMINEF stands for American American Indonesian Exchange Foundation. I believe there is also Fulbright in Malaysia because I met some people there sponsored by Fulbright, and almost every country had the program. And this Brian Howe was my supervisor at the University of Miami, and this the Steven Seeger from Australian Bureau of Meteorology. Uh, we included him because we use the source term we use in the model. So what I'm going to say now is motivation and model setup, and then the buoy locations. The always issue in the modeling is how much we trust the simulations, and one way to verify that by using the measurements, whether you do the official measurement, we do our own measurements, or we use the publicly available measurements, and then we validate the model, and we see the seasonal and monthly mean significant wave height. I'll talk about the significant wave height later on, and also wave and wind directions and swell and wind shear. So when we are talking about the swell here, that's actually we are talking about the surfing, and then we draw the summary, but I'm not sure how much time do I have for this. 40 minutes. Okay. All right. Thanks. So why the global model? They use why the global model in Indonesia, for example. If we are studying about the wave in Indonesia, then oops, sorry. The always the issue in Indonesia is we lack of observations. So that's the main issue. If we look at the observations, this is are the buoys deployed by the one company in US called SOFAR. They deploy all thousands of buoys around the world, but then still we miss some of the places. For example, Indonesia, this area, and those areas. And what actually we need is we need as high a resolution as possible. For example, if we do the wave prediction, we need to know how far the interpolation will be. For example, if we have the resolution 5 kilometer, actually means that in between 5 kilometer we just do the interpolation. While if we only rely on the observations, then we get the very coarse interpolations. So this is the observation conducted by the University of Miami. Some of them we call it the CLASI stand for constant land air sea interaction. And then, oh, okay. And then we are also talking about the satellite, altimeter satellites, for example, altimeter. I've been working with the University of Melbourne for about 6 years. We are working on the wave, wave measurements and wind speed from the satellites. And then the issue there is the also the resolution. If we see this the track of the satellite, and then if you look at in between the the resolution is very coarse. Indeed, for this the satellite, if you go along the path, and then we can actually get the resolution about 7 to 10 kilometers, but between the the track, that's very coarse. And so that's why we also talking about the coastal area, because why the coastal area? The coastal area is very challenging because even the satellite we also have some issue because of the land contaminations. So we are going to use the what we call it the model wave watch tree. This is the wave watch tree used in US for wave predictions. Also in Australia, I'm not sure what is used in Malaysia, but in Indonesia we also use similar to this, but they did a little bit modifications because we have so many islands there, and then they try to avoid the land contaminations. And what's the model here is so if you look at the model is also based on the what we call the wave exchange balance equations. But I'm not going to talk about the details of this because I assume that all of us are not in the real what you call computational mathematics, and this related to computational mathematics. And this is actually if we look at further, the first term is actually we call it the rate of net change of the wave actions, and F is the variance of density spectrum. So sometimes this model we call it the spectral wave model because we use the spectral in the model. And then there's also we call the affection of the wave action, and another term we call the propagation of speed in the wave number. So K here is the wave number, and also in the directions. And in the model, on the right hand side, we call it S dot. It's actually the total source term. In this case, we can apply input, dissipation, non-linear button frictions. This is the braking, and then this is a trace. Also, there is ice. And here, what people develop here is the S input. So in US, they call it the ST4. In Australia, they use the ST6. And here, we are going to use the ST6. So ST6 developed by the University of Melbourne. So I used to work at postdoc at the University of Melbourne for more than 2 years, and we are working on this topic. But so if you're interested, we can see the paper of Seeger et al. 2015. So that's but as I said, I'm not going to go through to the details. But if you're interested, then we can definitely discuss. Oh, sorry. Did I press wrong button? Okay. Sorry. Oh, okay. Let me try this. Yes. All right, let's see. I need to go in again there. I'm doing it. But I couldn't save. Okay. Okay. Now I get it. Like this. Different time. Okay. Accept that. And, uh, let me end that save. But the same thing. Then I'll save it the Windows. And once and then third and then it's all right. Thanks. All right. Sorry for the interruption. Okay. So let me go through this. Oh. No. Ah. All right. So how actually we did the calculations? We downscale the model. So from resolution about 50 kilometers, and then we went down to about 20 kilometers, and then we also went down to about 5 kilometers. And then because we are dealing with the coastal area, and then we had a very complex coastline, so we instead of using the regular grid, we use the unstructured grid. So this is what we have. So this is the unstructured grid. So if we look at this, very black one is actually means that very high resolution in that point. And then so the number of elements here is more than 100,000 elements and 50,000 nodes. So we use the supercomputer for these calculations. So my laptop cannot do this anymore because of the memory. And then what the mesh resolution we can see from here, uh, around the open boundary conditions, we use the about 2 kilometers, and then around the coastal area we have 150 meters. So we downgrade the resolution from 2 kilometers to 150 meters, and this is the uh, bathymetry, the sea floor or the depth of the oceans of the sea. And in order in order to generate this unstructured grid, we use this model. So this published about 5 years ago. It used to be very complicated, but by using this ocean mesh 2D, now it's quite simple. And then what the input of the model. If we're for the global, we include the wind and ice, but then for the grid, the high resolution we only use wind because there is no ice in California. If you've been to California, then you can see that there's no ice there. And also we have the bathymetry we get from here. The resolution of this bathymetry is about 500 meters. and this is the source of the wind. We call it from the NCAR. And source term used here is ST6. In US, they use the ST4. And this is the we also include the reflection because we are dealing with the coastal area, so the reflection on the shoreline should happen. And also we assume that the seafloor around around the California is sandy, so that's why we use the SOX bottom frictions. And what the output? There are many outputs from the model, but we're only interested in significant wave height, mean wave period, but the most important here is the peak frequency. And so what are if you are new in the ocean waves, what is the significant wave height? So the significant wave height is if we have the wave measurements about 120, we order the from the highest to the lowest, and then we take 1/3 of them. So if we have 120, then that means we take 40, and then we take the average. So that's what we call it, the significant wave height. So it's not the highest wave height, but that's this highest, the average of the 1/3 highest significant wave, high wave. And then one of the most important things is the delta t time step. If you are dealing with the numeric, and we also talking about the time step. And here the rules for the time step. So that's why we get the time steps. All this in seconds. So for the global, we'll have different time step. For the high resolution, it's very small time step. And there's the U. U stands for the University of Miami, because we perform the calculations at the University of Miami. And 1 month simulations here took about 10 hours using 160 processors. So we need about 250 gigabyte memory to calculate this. So that's why we need the supercomputer. And this is the win. I just keep this because this is the win from the we just check how good the win from the NCAR, and we can see the win is quite good for the directions, but the high wind speed is lower estimated by the model. And this is the buoy locations that I mentioned before. So this measurements conducted by the University of Miami, while the blue dots here is actually taken from the NDBC. NDBC belongs to the American measurements, and then there's one called the CDIP. CDIP buoys actually belongs to the coastal what you call it, one company in US just deployed the buoys around the coastal area. So that's we call the city buoys. And then so this is the classy here. We call it classy coastal land air sea interactions. This is the name of the project owned by the University of Miami. So they conduct the measurements at the locations about three phases: phase 1, phase 2, and then phase 3. Different months. They skip it. If we look at this, quite far from here to here, because here there was a storm in California, and they avoided the storm. And so that's a buoy that we are going to use for validations, and this is the statistical parameters that commonly used for buoy, the model verification. So how good these failures will how good the model can be measured by these statistical parameters. So this is a bias, RMSE, scatter index, and correlation coefficients. And once we have all of the model simulation done, and then we have the measurements, and now how do we perform the validation? So we take the wave height from the model, we take the wave height from the measurements, we have the what we call it the spatial time difference. So we assume, for example, just less than about 30 minutes, because if that they are too far, then actually the comparison will not be good. So once we make the comparisons, we can see here that this is the the wave height from the model, and this is the wave height from the buoy, and then the number of measurements here is about more than 84,000. So we can see here that the correlation coefficient uh, almost 1, do it means that they are good, and then the scatter index is less than 0.2, and the bias is 0.08, 0.06, which is very, meaning that the result from the model and the measurements are very, very close. That give us the confidence that our simulations is not doing, it doesn't go to the wrong place, because that's how do we validate it. And then this is for the NDBC model. They give us almost similar for from the city boy. Thanks. Okay. We also can see here that correlation coefficient it's about 0.9, and then scatter index less than 0.2, and the bias is 0, meaning that meaning that uh, the average difference between the model and the observations is about 12 centimeters, which is very, very small. And there always a question here is what is the best RMSE, or what is the acceptable RMSE? And in the significant wave height, we people in the community say that as long as that it doesn't offer uh, it's not over 0.5, meaning that 50 centimeters, that should be acceptable. But once they are over the 50 centimeters, then there will be the questionable. And this is also the direct observations conducted by University of Miami. Here, even though the correlation coefficient less than 0.9, but the RMS is 0.2, meaning that's about 21 centimeters. So we conduct the the comparison between the measurements and the model, and give us very good agreement between this model and the measurements, and then we say that okay, we are confident with the result, and if we are confident with the results, then we took one simulations in 2021 in October. So this is actually as we can see here that oops, sorry. Okay. So if you can see here, so this is the highest resolutions that we are interested in. So we believe that the reality in the reality in the around the California in 2021 is like this. And we also saw the seasonal mean significant wave height. And as you can see here, the highest is about March, April, and May. Then the lowest is what is this in August. And then we also check the mean significant wave height. Okay, so this is a monthly significant wave height. We can actually see here that this is in May. In May is the highest, and the lowest is in July. So that's a monthly. So I just saw 6 of those because of the time. And then we also check the wind directions in the California. So as you can see here, so this is the San Francisco here, and this we call the Monterey Bay. It's a very very attracting place to surf, and we can see here that based on the model observations, we can see that the wind directions mostly from the northwest, and also the wave directions also mostly from the northwest. So we can actually see from here because the waves are coming from the Alaska. And then, so this is the different time. Unfortunately, it's not very clear. And then the wave directions, compare the model. Here, this from the observations and this from the model. We did all for different time, and we can see that they are quite similar. Okay, now this is the most interesting one. So uh, I mean the most interesting result is actually the swell and sea. What we call it the swell, if we are in California and there is a storm around the southern hemisphere, for example, around New Zealand, and the waves are actually the storm are there, but the waves generating by storm are propagating through the Pacific and then arrive in California. That's we call it swell. Like in Indonesia, if there's a storm in the Indian Ocean in southern hemisphere, and the waves are propagating through Indian Ocean, and then the waves will be arriving in south of Java or Bali. That's why Bali is very good place for surfing. So if you go to Indonesia and then you would like to surf, don't go to the southern Kalimantan because the waves there is not really promising the for surfing. But if you go to the southern Bali, Java, and then what you call it, the west of Sumatra, the small island there, that will be a good place. Yeah, Padang. Okay, Padang. That will be a good place for surfing. And how do we learn uh, s- swell here? So as I said, the swell is generated by the storm far away, and then we get the swell there, and that means the period is very long. So we take that advantage of that period. So we assume that if the period more than 10 seconds. This is very, very, very coarse simplifications. So we assume that if the period is greater than 10 seconds, we assume that's swell. If less than 10 seconds, we assume the wind sea. Yeah, meaning, so wind sea is wave generated by the local wind. So if we go to the beach now, and then we can see this very irregular surface of the waves. That's actually most of them are, wind sea. But if we are standing in the beach, and then you can see the waves are coming very regular from the oceans, and then that's actually swell. So that's why if they are very high, and then the people who are surfer will be very happy with that. So how do we calculate? Then we take the spectrum. So we go through the spectrum, and then we calculate them. So this is every hour of the spectrum. So what we do here is, let's say, for example, here. So we assume that less than 0.1 will be swell, greater than 0.1 will be wind sea, and then we calculate the energy, the total energy of this spectrum. We calculate the total energy. How do we calculate? We use the integral. Okay, see. Actually, there is equations here. So simply what we do is we calculate this the total energy of the spectrum uh, using this integral, and then we convert it to the significant wave height with this formula. So that's how we convert it. We convert it to the significant wave heights from the spectrum going to the significant wave heights. And then we can get the significant wave heights like this. So this is the swell. We assume this is the swell, and this is the wind sea. If we uh, take all together, and then there's actually this wind sea and swell. So this is, for example, when I pick up very uh, one point, for example, at this time, as you can see, most of the spectrum under the 0.1 hertz. That actually means that the very high swell here. But here, for example, most of them are greater than 0.1. That actually means that wind C is very dominant. So uh, what this what this figure tell us, we can actually see that uh, if you're a good surfer, and then it's not good to go to the California during the June, July, August, because the swell there is not really good during the summer. But if you're if you're a beginner or want to learn like me, because I'm not a surfer, that probably that's a good time to go, because the waves is very, the swell is not really high, and then so it won't be very dangerous for me. But if you're an expert, and you can actually see that when we go December and in January, this is actually very promising one. That's only for the export or experience. And then during the April and May, because this is only one year data, during the April and May, actually, why is not interested? Because why is not interesting? Because the swell is not consistent. So sometimes comes very high, but then most time it's very low. So that's why people are not interested during the April and May. They just because inconsistency of the swell. So yeah, that's actually the how we take the advantage of the significant wave height to study this swell. And then when we compare how good our swell, we compare also with the significant wave with the observations. So the red one actually from the model, and the blue one from the observation. So we can see here that they are very close. But if we take all of them, then it's quite difficult to make a decisions. So we follow the previous method, and we also perform the matchup. So this is what we call it, the matchup. We match between the model and the observations, and we see the statistics. If the statistics is very good, that actually we say, oh, the model's doing well. Otherwise, the model just gives the number, or it doesn't actually give us the advantage. So in this case, we actually divided the spectrum into the frequency into 4 different groups. So the first is between below 0.06, and then from below 0.9, and then 0 below between 0.9 and 0.2, and then above 0.2. So we can see here the local wind is very low. It's just about 2 meters. But if you look at the here the swell, they can get up to 4 meters. Okay. All right. So we perform all of the different measurements, and we get the we get a similar result. So we assume we are confident that the model doing well. Let me draw the summary. In Monterey Bay, wind and waves are predominantly originate from the northwest, as I mentioned before. And then swell activity generally low intensity during the summer, but very good for the beginner. So if you like to learn surfing, and then it's probably good. In autumn, September to November, uh, become more consistent. So this is actually the best for the surfing, and also for the experience. if you're experienced surfer, and then you can go for December to February. As I mentioned before, so during the March, April, and May, the swell is not very consistent, so we don't recommend you to go for surfing at that time. Thank you very much.
Okay, thank you to Dr. Ribal for the nice presentation. So now I open for the Q&A from the floor.
Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon. All right, my first question is, why California, not Bali? Because Bali also is known as a common place for surfing. And then if you have did same study at Bali, so what kinds of the patterns that you found in Bali compared to California? What is the difference?
All right, thanks. That's very good question. So before I went to California, Miami, I asked that question to my supervisor because University of Miami is in Florida, and then the observation site is in California. So that's at the time, and then I asked him why you need to spend money from fly from Miami to San Francisco just to conduct the observations. And then there are a few things that he explained to me. The first is in Monterey Bay, it's very attractive swell. So the swell could come from the northwest, actually from Alaska, and also the swell are coming from the New Zealand. So if there is a storm there, and then they always go to the California. And then there's a paper published by my supervisor in Australia. He actually can make the map where if there is a storm in southern hemisphere, where the swell will propagate, and eventually they all go to the California. If you ask me why, and then the wind will make it, and so I don't know why wind blow that way. So that's the first questions. I hope I answered that. Okay. And the second question is what we did in Bali. In Bali, actually, we didn't actually concentrate on swell. So we were concentrating on wave energy. So we simulate for all the Indonesian ocean with a resolution of 5 kilometers, collaborating with the University of Melbourne and also Australian Bureau of Meteorology, because the Australian Bureau of Meteorology will provide us the supercomputer to perform the calculations. But late in the future, we plan to study the entire Indonesia, and then we can actually can make the map when actually the best time to go to Bali for surfing. But that will be the future work. All right. Thanks. I hope I answered the question. Thanks.
Ya, kita sama-sama dari delegasi yang sama, dan saya sangat terkesan dengan ini. Ceritanya ini kan kita lagi di Malacca Peninsula ya. Kita jauh-jauh tadi melihat ke mana California. Tentu saja ada tempat yang dari kajian Pak Ribal ya, yang kita bisa mapping di mana di peninsula ini tempat yang kira-kira mirip dengan California, karena kan ada bagian dari peninsula ini yang juga menghadap ke Pasifik ya.
Yeah, northeast.
Northeast, right?
Northeast. Yeah.
Yes.
Exactly.
But yeah, if you use the idea of the California that you present to us, and we look at the world map that you show us before in some slides in your presentation, can you give us some idea that for the location that, which the analogy that you use for the California case, that we can assume that in the Malacca Peninsula there are some points there. Yeah, I saw the Perlis. There is a Pulau Langkawi there, and remind us also Makassar. In Makassar, see, we call it Spermonde Archipelago. There are around 100 Somali islands there, and we know the islands tend to break the big waves, which is no longer good for surfing actually, because all waves coming, which is good for surfing, it's already break because of the existence of these islands. But it's good to some extent because those small islands also is a big water for the if there is a tsunami. Yeah? So, Ribal, again, my simple question is: could you give us some idea where is a good place for saving in this peninsula? Thank you very much.
All right, thanks. If you look at this map, but it's not, hopefully it's quite clear. If you look at it, we are here, right, in peninsula. And then the thing is we are blocking by the way, the islands. So I'm not sure if we can get it here. For example, the island, the sea between the Sumatra and peninsula. So the waves are blocked by the Sumatra island. So I don't think there's a place, the good place to surf there. But for the eastern part, for example, here, if you're lucky, and then you can actually get some of it from here, but it's very low. It's only occur about in January during the winter in the northern hemisphere. So the waves are coming from Pacific, but then again, because the waves are blocked by are blocking by the waves are blocked by the Japan. So that's actually makes waves being trapped. But the most interesting thing there is if we are interested in wave ocean current, and that the place is very good. So so here, wave current here is very strong. So we did that few years ago, and we can find that so the the ocean between the islands, the waves is not good, but the current is very promising. So that's that yeah, that's say again. Sure. Exactly. So if the wave is very low, and then we say let's look the current, because Indonesia, for example, we know what we call it the Indonesian true flow. So that's why in the because the waves are propagating from Pacific through Indonesia to southern hemisphere, and that's in Japan. The most famous current in Japan, we call it the Kuroshio current. That's a very strong current in Japan. All right, I hope they answered. Okay. No, no. Exactly. Yeah, yeah. Sure. Yeah, I think I agree. Exactly. So that's why I'm saying that that's only good for the beginner. Yes, if you want to learn how to surf, and then maybe that's a good time to go. Yeah. All right. All right. Thank you very much for that.
Okay. Dr. Ribal for the presentation and the Q&A. Now I would like to welcome Professor Madya Dr. Khairul Anwar Ghazali, Deputy Director of Academic, to give the token of appreciation to our speaker, Dr. Agustinus Ribal. Mana? Sini? Depan? Sana? Sini? Mana? Sana lah ada. Okay, Ribal. Gambar-gambar kita sama. Alhamdulillah. Okay. Thanks again to Dr. Ribal and Dr. Khairul Anwar. Okay, any? No. Pak Khairul? Ada lagi? Untuk saja. Okay. Sebagai kata penutup lah. Okay, saya persilakan Dr. Pak Khairuddin untuk memberi sedikit ucapan penutup.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirrabbilalamin. Kita telah melalui beberapa tahapan pada pertemuan hari ini dan we gain lots of things. We are honored to be here and melihat terima kasih atas great hospitality dari tuan rumah, dari host sekali lagi. Dan kami insyaallah selanjutnya akan menindaklanjuti ya apa yang telah kita sepakati bersama pada pertemuan hari ini, dan mungkin akan ada pengembangan kerjasama atau new collaboration, extension of this collaboration today, not only from mathematics and statistics but also physics department insyaallah. And also we are looking forward to see most of you in Makassar next time, insyaallah. To visit us in a big delegation like this one we have here now. Thank you very much once again. Insyaallah mudah-mudahan Allah memberikan petunjuknya pada kita semua, diberi kesehatan ke depan. Terima kasih sekali lagi kepada Dr. Zuki, especially for Prof Ismail. Ya, terima kasih, dan Bapak Ibu pensyarah dari IMK. Terima kasih Pak Dokter. Ya, terima kasih banyak sekali lagi. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, ada dari IMK. Ada nak balas ke? Tak ada. Okay, kita dah hampir ke penghujung majlis kita. Cuma Bapak Ismail, saya tengok di atas mejanya itu ada beberapa proposal katanya. Kalau ada satu aja. Kalau ada Bapak dosen daripada Unhas yang mau kerjasama sama Pak Ismail, proposalnya sudah siap. Buat aja lah, kan? Proposalnya sudah ada, dikerjakan saja. Okay. Okay, saya rasa sikit. Jangan lama lah nak bagi haknya ni.
Terima kasih. Assalamualaikum warahmatullahi wabarakatuh. Allahumma salli ala Muhammad wa ala Muhammad. Saya baru datang dari Jakarta, UGM. Saya bertang satu proposal projek master dan sarjana. Master 1 tahun. Sarjana 3 tahun. PhD 3 tahun setengah. Setengah itu main-main. 3 tahun yang pastinya insyaAllah. Model ini model baru diperkenalkan tahun 20. New steepest descent. Dan disiapkan 43 references.